In this video, I want to present the basis of some group theory, irreducible representations, and tensor products. And all of this is useful to build equivariance neural networks. So in this talk, I will introduce this math notation about groups and irreducible representation, but especially for rotation and parity. I will not talk about translations. And second, I will show how to manipulate equivariant function, in particular polynomials, which will be useful to compute spherical harmonics. I will show an example of that. Then it's also useful to create invariant polynomials, and it will be presented by Thomas and Martin in their talk today as well. And it's also useful to create the linear part of equivariant neural networks. And then I will talk quickly about nonlinearities, how to make nonlinearities in neural networks. That is equivariant. So this talk is split in 3 parts. So first part, I will define equivariant polynomials and give the tool to create these equivariant polynomials. In the second part, I will show 3 examples on how to use this tool to create equivariant polynomials. I will show code. And the last part, I will talk about how to make gates, which is an example of nonlinearities. So before talking about polynomials, I need to introduce quickly some notion of group theory and representations. So a group defines a set of operations and how these operations compose together. And representation defines how the group acts on some vector space. In our case, the group we will talk about will be rotation, parity, and potentially rotations, but not in this talk. And the representation will be, for instance, scalars, vectors, pseudovectors, stuff like that. So here is the mathematical definition of a group. It's a set of transformation that contains the identity. This set must contain transformations that are stable. So if you compose one transformation with another of the group, the composition of the two has to be in the group as well. And you need an inverse. For each element of the group, you need the inverse transformation to also belong to the group. And then a representation tells you how, for some element of the group, how it acts on some element of some vector space V. So d of gx is the transformation of x by g on this particular vector space. It has to be linear in the parameter the x. So if you apply it to x plus y, it's the same as applying it to x and y separately and sum together. And it has to follow the same structure as the group. So if you want to apply the composition gh to x, it has to be equal to applying first h to x and then applying g after. There is an equivalent notation where instead of writing d of j and x, you write it as d of j, which then is a matrix that you can then apply on x. So d of j is a linear operation from v to v, so we can write it as a matrix. And then this constraint can be then written as matrix multiplication. So the matrix of GH is equal to the matrix of G times the matrix of H. So we will use this second notation in the code and in the future slides. So let's take an example of a representation. Let's say we have 9 real numbers. And let's say that the 3 first are scalars. So a representation is like a data type. It will tell you how to interpret the data when there is a rotation that is acting on your system. It does not tell you what these numbers are, what they represent, but at least you know how rotation acts on them. So if you know that these 3 numbers are scalars, it means that if there is a rotation acting on your system, these 3 numbers will not change. Then let's say that the 3 next are vectors. So if you rotate the system, these 3 numbers will change together. And let's say the 3 last are also a vector. So each of the 2 vectors transform independently. If you know the component of one vector, you will know how it will transform, but you don't need to know the component of the other vector. So when you apply a rotation to the system, let's say G, then this representation will transform as the vector times the matrix D of G. And this matrix will have the following form. It will be block diagonal. It will have 1 for the scalars and a rotation matrix of size 3 times 3 for the vector. And outside it's all zeros because, for instance, if you take this 0 here, it means that this scalar A2 will not affect the new value of A3. And these zeros here means that these 3 last numbers, the last vector, will not affect the first vector. So in e3nn, we represent this representation with a string, and we write it like that. 3x 0e means 3 times scalar. 0e is for scalar, and then 2x 10 means 2 times vector. So I will explain later why 0 is scalar and 1 is vector. And we have a class that is called Irreps. You can call this class by giving that string. It will parse it. And it is useful, for instance, to compute this matrix D of G. So here we just generate 3 random angles, alpha, beta, and gamma. And these are the Euler angles. They describe a rotation. If you want, they describe G. And we call irreps.d from angles, and we give the angles. And this will compute this matrix for that particular representation. And as you can see, we get the block diagonal form as expected. And you can see also that these 2 rotation matrix for the 2 vectors are identical because they are exactly the same representation. Now, let's define what is equivariance. So let's say you have 2 vector space, V and V prime, and on each of these 2 vector space, you have 2 different representations. On V, you have the representation D, and on V prime, you have the representation D prime. So the representation, when you act with the representation, you stay in the same vector space. This is why it's at the end of the arrow, it's also v, and here at the end of the arrow, it's also v prime. And now let's define, let's say you have a function that takes an element in v and send it to an element in v prime. We can also write f on the bottom because it's the same vector space. And now let's say we transform our system with a rotation, and we can either first transform the system with the rotation. So we take an x that is in x in v, and we apply it the representation d of g, and then we apply the function. So we get the following expression. Or one could also first apply the function, then we get an object f of x that is in v prime, and then we rotate the system with g. So this object will be multiplied by the matrix d prime of g. And the function f is said to be equivariant if the two options lead to the same result. One can also say differently that the action on the group commutes with f. But be careful because outside of f, you have to act with d prime that acts on the output space. And inside of f, you have to act with d that acts on the input space of f. So now let's see how we can create polynomials that are equivariant for the group of rotations. Why polynomials? Because they are the most simple function in math, but yet they are very powerful because we can approximate many functions with polynomials. So what do I mean by polynomials? So polynomials are function of this form, like x squared plus 2 times x minus 4. And I want to generalize just this a little bit. I will consider polynomials of multiple arguments, like for instance, x, y, and z. So this polynomial mix x and y and z together. And to be even a little bit more general, I want to consider, I will call as polynomial a function that takes many arguments and might also return many polynomials into a vector. I will call that whole function a polynomial as well in this talk. So an equivariant polynomial is simply one in which the representation of the input commutes with the polynomial. So this polynomial, for instance, is not equivariant, assuming x, y, z are the component of a vector, because if you rotate this vector, then this output will not transform as a representation. And rather than this example of polynomial is equivariant, x squared plus y squared plus z squared gives you the norm square of the vector, and it is a scalar. So if you rotate the input vector, the norm will not change. So this is an example of an equivariant polynomial. More specifically, this one is invariant. So here is the 3 tools that will allow you to create equivariant polynomials. The first is composition, then addition, and then multiplication. With these 3 tools, you can create any equivariant polynomials. So let's start with the composition. And it's simply that the composition of 2 equivariant functions is equivariant. So if you go through the math, so if you take h of f of d1 of x, since f is equivariant, you can replace d1 of g by d2 of g, but applied to the output f of x. And then again, since h is equivariant, you can do the same and get d3 of g outside. And if you discard the middle step, if you look for only the first and the last step, this is exactly what we need to say that the composition of H and F is equivariant. Second tool is the addition. And it means simply that the addition of two functions that is equivariant is also equivariant. And same idea. So if you rotate the input of both functions, since both functions are equivariant, you can pull out the rotation, and you can factorize and get the representation outside, because the representation is linear. So here we use that it's F and H are equivariant, and then that all the representation are linear. Now let's talk about the more complex part, which is the multiplication. So let's say x1, x2, x3 transform with the representation d of g, and this other vector transform with the representation d prime of g. It turns out that if we multiply all the possibilities, so x1, y1, x1, y2, x1, y3, and so on, and we put them into a matrix like that, this operation that is called the tensor product is equivariant. And this matrix transforms with a representation that is called the tensor product of the two representations. And you can show mathematically that this is a representation. As you can see in this example, the dimension of the tensor product of two representations is equal to the product of the dimension of the two representations. So are we done with these three tools? Can we make all polynomials? So yes, we can create at least all the polynomials that are called the Cartesian tensors. So, and they are made of vector times vector times vector. So the Cartesian tensor are of shape 3 times 3 times 3, and so on. The little problem with manipulating Cartesian tensor is that they grow in dimension every time you multiply them by another vector. And this is problematic to create neural networks, because we don't want that at each layer we get our features, number of features multiplied by 3. But luckily, these tensor products are reducible. So what does it mean to be reducible? So a representation is said to be reducible if it exists a subvector space such that if you restrict this representation to that subvector space, this restriction is a representation. Let's take this famous example of the tensor product of two vectors. This is the matrix, and I will show you that this matrix can be decomposed into smaller vector spaces in which the representation is still a representation. First, you have the trace. So the trace of this matrix is a subvector space, and it is a representation because you might recognize here the scalar product, and the scalar product of two vectors is a scalar. By that I mean that if you rotate the two vectors, the scalar product stays the same. Then you have the anti-symmetric part of the matrix. And if you write it like that, you will see that it's nothing else than the cross product of two vectors. And same, the cross product is a representation because if you rotate the two vectors, the cross product of the two vectors will also rotate. So this is a vector, the cross product. And the remaining degrees of freedom, which there is 5 of them, and represent the symmetric traceless part of this matrix, is actually also a representation. And it happened that all these 3 representations that we found into this 3x3 matrix cannot be reduced anymore. So usually we write down to describe what we just did here, this expression 3 times 3 equal 1 plus 3 plus 5. And what does it mean? It's that if you have a vector, a dimension 3 object, times another vector of dimension 3, you get a matrix of 9 elements. And these 9 degrees of freedom can be decomposed into 1 degree of freedom, which is this trace or scalar product, 3 degrees of freedom, which is the antisymmetric part or the vector product, and the 5 last degrees of freedom, which is the symmetric traceless part. All of those can be seen as polynomials. So we have here 3 equivariant polynomials of 2 input vectors. So these are polynomials of 6 arguments. So representation that cannot be reduced are called irreducible, and we know which are all the irreducible representation of rotation. They are indexed by L, usually in the textbooks, and L is an integer that goes from 0 to infinity, and for each of these L you have one irreducible representation, and it is of dimension 2L plus 1. L equals 0 has dimension 1, and these are called the scalars. L equal 1 has dimension 3, and these are called the vector. L equal 2 has dimension 5, but there is no name for describing it. But now if you add parity to the rotation, you get a group called O3. And what you get just 2 times more irreducible representation. They are still indexed by L, but you have the even ones and the odd ones. The L equals 0 even representation is called scalar, and the L equal 1 representation is called pseudo vector. The even representation are the one that don't change sign if you apply the parity, and the odd representation are the one that change sign if you apply the parity. And a vector, for instance, change sign if you apply parity. So it's an odd representation. And the pseudo scalar, it's a scalar that does not change sign if you apply parity. Sorry, that does change sign if you apply parity. So it is also odd. There is a theorem to tell you how to decompose the tensor product of 2 irreducible representations. And it goes as follows. If you take the tensor product of a representation L1 with a representation L2, it can be decomposed into all the representation between the absolute value of L1 minus L2 and the sum of L1 plus L2. So if we just take examples, L equal 2 tensor product with L equal 1 can be decomposed into L equal 1, L equal 2, and L equal 3. And for instance, 2 tensor product with 2 can be decomposed into 0 plus 1 plus 2 plus 3 plus 4. It's a generalization of the 3 times 3 equal 1 plus 3 plus 5. Be careful in this formula below. We write the dimensions, and here we wrote L. So these 3 correspond to vectors. So it corresponds to the L equal 1, and this one corresponds to a scalar, so it corresponds to L equals 0. So this expression, but written with L, would be one tensor product with 1 equal 0 plus 1 plus 2. So now we saw these three tools that allow to do equivariant polynomials. So now let's see example with codes. So to implement in code the composition, you just compose the function. And to implement the addition, you just add the output of the function. But to implement the multiplication, we wrote some classes in Python working with PyTorch that allow to do these tensor products. So let's start with the first example, spherical harmonics. So spherical harmonics are polynomials, and they are the highest representation of the Cartesian tensor of x multiplied by itself L times. So if you look into this graph, on the x-axis you have the degree of the polynomial, and on the y-axis you have the order of the representation. And if you consider a vector x, it's just the vector x itself. You can see it as a polynomial of degree 1, it's the identity. And it is a representation of L equal 1. And this is actually the spherical harmonics L equal 1. It's just the identity. Then if you multiply x by itself, you will get the norm square, the cross product of x with itself, which is actually 0, and an L equal 2 representation. And this L equal 2 representation is the spherical harmonics of degree 2. And then you can continue, take this representation and multiply it by x again. You can then decompose what you will get in also three representation. One here that will be a representation L equal 1. One here in the middle that will be equal to 0. And one that will be a representation L equal 3. And it will be the spherical harmonics L equal 3. And you can continue like that. So let's see how to do that in code. I just create a Python notebook, and I import e3nn. So e3nn is made of submodules. There is O3, that is the principal submodule that contains all the operation to deal with rotation and parity. And then there is also NN and IO, that NN is to make neural networks with e3nn, and IO is to deal with some specific format of data. And I will also import PyTorch. So to create the following tensor product, so vector times vector, we can use the class full tensor product and give it a vector which is 1 O, 1 correspond to L equal 1 and O to odd, times another vector, and we can print what it shows. So it prints that vector times vector gives you a scalar, a vector, and an L equal 2. So we can just test it. If we do TP of torch dot tensor, let's give him some floating points. It returns you 9 numbers. And we can now restrict, because to do the spherical harmonics, we need only the highest degree. So we can tell him to only output Ereps 2e. So this is the L equal 2 component of this vector times this vector. If you want it to correspond to the symmetric traceless part of the tensor product. And this is nothing else than the spherical harmonics if the two vectors are equal. So if you want, we can define spherical harmonics of degree 2 of some vector x, which is simply the tensor product of x with itself. And now, if we want to do the L equal 3 spherical harmonics, we can compute the L equal 2 with spherical harmonics 2, and then do the tensor product of what we just got, which is an representation 2e times a vector times x, and we will only keep the 3o part of it, which is the highest representation in it. So we can just check that it executes correctly. And we can check that it is equivariant. So if we define the input and output Ereps, input is just a vector 1o, and the output is 3o. So if we define Euler angles, there's a function called round angles that creates random Euler angles uniformly distributed on the space of rotation. So here we have 3 Euler angles in radia, and we can take Ereps in and do d from angles and give the angles, or input Ereps out and get the matrix. So to check that it is equivariant, we just create random inputs. Let's say 100 input vectors. So the shape of x, it's -1. Shape of x is 100 times 3. -1 means that we want to put the Erep index here, and Ereps in is just a vector, so it will be 3, the dimension. We can get the dimension of an Ereps with just the dim. And now we can feed this input to spherical harmonics, and we get 100 vector of dimension 7. So to check that it's equivariant, we need to apply the rotation first and after, and check that the two give the same result. So let's apply the rotation first. ij will be the rotation matrix, zj, and we output zi. And now let's rotate second. So out2 is equal to torch.einsom. So we use now ereps out, and as input we take the spherical harmonics of x. And if spherical harmonics is equivariant and we did no mistake, out1 must be equal to out2. Okay, so now let's move to the next example, which are the tensor products, but with weights. So if we go back to this example of a vector times a vector that we can decompose into scalar, vector, and L equal 2, we can keep only one of the three output reps. Okay, forget what I just said. So we can represent this operation with this figure, where here you have the input, the first input, and here you have the second input. So you have the two vectors. They are multiplied together, and here you get the three outputs, the scalar, the vector, and the L equal 2. And when we put weights into our tensor product, we can do things like that. So let's say you have three input vectors and three input vectors, and you make all the multiplication of this three vector with this three vector. You get all the intersection here that correspond to one tensor product. And let's say you want as output also three pseudo vectors, 1e, and you use weights to sum, to make weight sum of all the tensor product you have here. So this third pseudo vector will be a sum, a weighted sum of all the 9 possible cross products you have here. And each of the output vector has its own weights. So they have each 9 weights. So there is in total 27 parameters. So if we do that in code, I will keep this same notebook. It's with the class fully connected. So if we just do full tensor product, the original one, with tp.visualize, you can generate these kinds of images. And now you can just take the vector output, and with another class that is called fully connected tensor product, you can multiply your two vectors and get one pseudo vector as output. But this time, this tensor product will have a weight. As you can see here, there is one path and one weight. And if you put two input vectors, both sides, You can see the different paths. Show weights. Plot weights. But this is not very efficient because it will do all the 4 tensor products independently, and we can instead write it like that: 2x10 and 2x10. Yeah. These two tensor products perform the same operation, but this one is more efficient. And this kind of operation is very useful to do neural networks, because this tensor product TP is a PyTorch module with parameters. And you can have access to the parameters. It's just weights. So the last example is how to reduce automatically Cartesian tensor that has some symmetry of the indices. For example, if you consider the inertia tensor is an integral over the body, rigid body with some density. And the formula is the following one, and it measures how easy it is to rotate that rigid body around all the different axes. And as you can see, this tensor is symmetric if you reverse the two indices. So ij is equal to iji. And we can, we have a class that is called reduced tensor product. And you can write it, write the symmetry of the indices in it. So ij equal ji, and you define that I is a vector. And it will compute on the decomposition into the symmetric part. So if you give him as argument the two vectors, it will compute the symmetric part. It also contains the change of basis. which is of shape 6 times 3 times 3. You can as well just get the irreps of the output, a scalar and an L equal to. And if we make another example, the stress tensor. So the stress tensor has 4 indices. Let's write them ij, kl. And if it has 2 symmetries, you can permute I and j, or you can permute ij with kl. So it's the same as kl ij, and other symmetry that we can get just by composing these 2 symmetries. And if you decompose that tensor, it contains 2 scalar, 2 L equal 2, and 1 L equal 4. And it has 21 degrees of freedom. Even though the first tensor originally has 81 numbers, there is actually only 21 degrees of freedom. So finally, let me just talk to you about how to make nonlinearities for neural network. So more specifically, non-polynomial operation. Because if a neural network is made only of polynomial, it does not train well. And the simplest way to do it is called the gate. And to do so, you just take 2 polynomials, P and Q. P is an invariant polynomial, meaning that the output of P are scalars. And phi is a function like, for instance, the sigmoid works very well. So you can apply the sigmoid on the scalar you get from P. And Q is an equivariant polynomial. And so you multiply the sigmoid with the equivariant polynomial, and you get an operation that is not polynomial, but still is equivariant. So I'm done. So the conclusion is that I presented you the basic group, the theory of group, and the representations. I defined what is equivariance, and I showed you that the composition and addition of equivariant function is equivariant. And then to create polynomials, I explained you that the tensor product allows to multiply irreps together. And I gave you the theorem for the rotation that tells you how to decompose L1 tensor product with L2. Finally, I show that we can make polynomials with weights and nonlinearities with gates. And these 2 things allows you to make neural networks. So thank you very much for listening.